So, and thank you for inviting me to give this lecture about superconducting RF devices for quantum applications. And I'm aware that I am now, this is last lecture just before the dinner. So I will try to keep, I will try to stick to the schedule. And if you have any questions, so please interrupt me anytime. You don't need to wait till the end of the lecture. So I will first give some introduction about superconductivity in general, and then Josephson junctions. And then I will explain very briefly about RF modeling of superconductors. Then talk about some superconducting qubits and control. Actually, the content of this talk is a 3-semester course, but I will try to give very brief ideas, and then for details, you can contact me or study the relevant detailed books. So we are located in Ankara, in TÜBİTAK Technology Center. And we have a group of 3 professors and about 10 other researchers, including students and foreign researchers. We have some cryogenic test capabilities, including cryo packaging and 45 Kelvin systems and 4 Kelvin systems and a 10 millikelvin dilution refrigerator system that was recently delivered, and also the peripheral electronics. So I will come back to this slide at the end of the talk, because for each picture I will explain how do we design the circuits and how do we design RF circuits in superconducting materials. But basically, the design workflow starts with the modeling of the basic building elements in a superconducting quantum circuit design. So it can be a passive element, or it can be some active circuit, including Josephson junctions. And then after the modeling, the layout and circuit models are generated, and they are drawn in some commercial VLSI tools, and they are fabricated. And after that, they are cryopacked and measured at cryogenic temperatures. So what is superconductivity and what is special with Josephson junctions? As we know, normal conductors are resistive elements, because the current is transferred with the help of outer shell electrons in the conductors, which are loosely bound to the atoms, and then they can freely move inside the metal. In general, metals are good conductors, and the resistance is generated when the current flows through a normal metal or normal material, and because there are repulsion of electrons between each other, the atoms vibrate, and there may be some impurities in the material. So the movement of the electron inside a conductor is a function of temperature. At higher temperatures, there are more vibrations and hence more resistance. And then the electrical energy is dissipated as heat due to the collisions of atoms or electrons scattering. But in the case of superconductors, we can talk about absolute zero resistance. In 1908, after the Kamerlingh Onnes liquefied the helium, they started to measure the resistances of different materials. And during one measurement in 1911, they measured the mercury. Actually, their assistants measured the mercury, and they found that the resistance of the mercury was below their experimental setup precision. So they repeated the measurements many times, and then they realized it's not an experimental artifact, but it's actually a zero resistance state. And then 2 years later, they got the Nobel Prize in physics. At that time, there were two theories about the resistance versus temperature of metals. One theory was if we cool the temperature, if we cool the material, the resistance will decrease, but there will be some finite value. And another theory was claiming that there will be after some critical temperature, the resistance were going to go to zero. And then after the demonstration of Kamerlingh Onnes, this superconducting, this theory was confirmed. So now at that time, everyone accepted. And then when they published the paper, actually in 1911, the title of their paper was Possible Superconductivity Effect. They put some tolerance that they still might be doing something wrong. Maybe you remember last year, some Korean group claimed that they found room temperature superconductivity. So each time some group finds some superconducting material at high temperatures or some undiscovered temperatures, so people are always suspicious. And at that time, Kamerlingh Onnes was also suspicious, but they proved to be true. And here, in this graph, one parameter was the critical temperature, but only critical temperature is not enough for a superconducting state. For a material to be superconducting, two other parameters should be satisfied. One is the critical current density. Another one is the critical magnetic field. So for a material to become superconducting, it should be below some critical magnetic field, below some critical current density, and below some critical temperature. So in this blue sphere, in this quadrant, material is superconducting for the case of high temperature superconductors or type T superconductors, and for the case of low temperature superconductors, it has to be below this gray area. Then why is some of the materials like niobium or aluminum or mercury, they are metallic materials? So why some metals are normal conductor and some other materials are superconductor? We can visualize how it is possible with these pictures. For example, in this left top picture, there is a pedestrian crossing, but without any organization. So the pedestrians hit each other and they move slowly. Or in an Indian highway, or maybe Pakistani highway sometimes, we see such crowded cars, or maybe in Istanbul also, such crowded cars, and they move very slowly. But in the case of right top picture, when the soldiers are marching with some tempo, then even if the density, the people density is similar, then they don't collide each other and they move more fast without any collision. Or in the case of highway. So superconductors, the movement of superconducting electrons or Cooper pairs can be visualized by these right pictures. And there exists a macroscopic quantum wave function in a superconducting material defined by PC that describes the behavior of the entire ensemble of super electrons in a superconductor. So all the super electrons are in phase and move in an ensemble, and they don't collide. This is explained by BCS theory. Also, Bardeen, Cooper, and Schrieffer got the Nobel Prize because they explained this superconducting behavior in the materials. So please keep in mind that in a superconducting material, there is only one wave function that you can represent the material properties. So this explains the zero resistance case. So there is no collision in the superelectrons. They can move freely. But zero resistance is not enough to define some material as a superconductor. There needs to be some other properties. One of the other properties is the Meissner effect. That says that in superconductor there cannot be a magnetic field. Even in a metal or in some other dielectrics, magnetic field can penetrate. But especially in type 1 superconductors, it's a perfect diamagnet and no magnetic field can penetrate. In the case of type 2 superconductors, some flux can penetrate with some organization, regularity. And in that case, some vortices occur, and this the region of this magnetic vortices behave like normal superconductor. There is a circulating current here, but the total magnetic field inside the superconductor is still zero. And one magnetic field is called fluxon in this case. Another property of a superconducting material is there is a quantum wave described in the electrons, as I explained, and this single wave corresponds to all the electrons, and that wave has a phase. So the phase has to be continuous. When there is a hole inside the superconductor, I mean, when we make a ring from a superconducting materials, the phase variation must follow certain rules like quantization. It means only some discrete amounts of magnetic field can penetrate this ring. Half or some fraction of magnetic flux quanta cannot be alive in the ring, superconducting ring. Then the superconducting material, if you apply some fraction of a superconducting single flux quantum, then the circulating current is generated in the ring, and then this discrete amount of flux quanta requirement is satisfied. So that's why, so for a material to be called as a superconductor, the flux quantization, Meissner effect, and zero resistance case should be observed. So we will use these properties in the following slides. Hence, we say that superconductivity is a macroscopic quantum phenomenon. We can put some analogy in photonics. In an optical fiber loop, the quantized wavelengths can be only allowed to propagate inside the fiber. In this case, in the superconducting loop, quantized magnetic flux can penetrate. And another Nobel Prize was given for the discovery of Josephson effect. It was discovered by Brian Josephson during his PhD studies, and he's among the youngest student to get youngest person to get a Nobel Prize at the age of 26. Josephson effect predicts two wave functions in two different superconductors when they are weakly coupled. So if we have a superconducting material on the left side, another material on the right side, and there is a barrier, very thin barrier in between, then the wave function on the left side and on the wave function on the right side is slightly coupled. So then the K is the coupling coefficient between two wave functions. That if we solve these two equations, coupled Schrödinger equations, we obtain two equations, AC and DC Josephson equations. One is this DC Josephson effect, and this is the AC Josephson effect. This predicts the DC current on the Josephson junction, and this predicts the oscillations on the Josephson junction. This means when you apply some voltage between these two superconducting sides, then there is an oscillation in between. So by using this property, for example, a very high frequency microwave generators can be made up, maybe terahertz sources, etc., can be developed with this AC Josephson effect. So some unique properties of Josephson junction enable the researchers to make macro scale artificial atoms. Now, in a linear LC oscillator, just usual LC oscillator, at different resonance frequencies, we get some energy levels. But since this is a linear linear material, both capacitor and inductor is linear, then the energy separations between different states are equal. And we cannot differentiate states between 0 or 1, 2, etc. But when we replace the inductor with a Josephson junction, then this circuit becomes a nonlinear LC oscillator or anharmonic oscillator. In this case, the energy levels are not energy levels are not equally spaced. So the distance between 0 state and 1 state is different from 1 state to 2 states. Because this is achieved because the Josephson inductance. So when these two equations, AC and DC Josephson equations, are solved, we get a inductance which is non-linearly dependent to the current flowing through the junction or magnetic field penetrating the Josephson junction. So there is a non-linear element here. That non-linear element means it has some atom-like behavior. We can use Josephson junctions to create artificial atoms. Then and in the next step, when we design superconducting RF devices, one critical element is Josephson junction, but other critical element is the inductors and transmission lines. In semiconductor circuits, inductors are usually ignored and they are considered as parasitic elements, and the circuit elements are mainly based on capacitors. Since it's a voltage-based circuit in semiconductors, in the case of superconductors, the circuits are based on currents. So inductors are the important element and capacitors are parasitic elements in general. So when we design an RF circuit, we can use commercial RF design tools like HFFS or Cadence or CST, etc., or other open source material, open source software. But unfortunately, in the libraries, in the material libraries of such tools, only the normal metals and normal materials are available most of the time. Recently, in the last few years, they started to include superconducting materials, but so far there were only normal metals. The difference between a superconducting, for example, a superconducting transmission line and normal transmission line, we should include the surface impedance when we design an RF circuit, RF device by using superconducting materials. Because since there is no surface impedance model in the available tools, we can use the Matisse-Bardin equations that estimates the surface impedance of the superconducting thin films, and then use these equations as a boundary condition in the, for example, HFFS or CST. And then if we can find the correct parameters, the estimation, experimental and model almost perfectly fit to each other. So we should make some iterations to find the correct parameters with experimental and experimental verification. But once it is available, once these parameters are available, there is no difference between designing a RF component between a normal metal and a superconducting material. So in this case, we assumed the model is developed for at 0 Kelvin, 4.2 Kelvin, and 8 Kelvin. But also we can include the critical current at different critical currents flowing through the material, because the critical current also affects the degree of superconductivity. So then we can make a multi-physics modeling that includes the critical current, magnetic field, and the temperature. And then it's possible to extract the kinetic inductance and the surface impedance of the superconducting material. In this case, for example, a coplanar waveguide is modeled or microstrip line is modeled. And here, for example, the inductance is extracted by using HFFS. But there are also some tools that only extracts the inductance, like Inductex. So you define the layer, you give the layer definition file of your fabrication process, and then GDS and circuit model, and then the inductance is extracted. This is similar to extraction of capacitors in CMOS circuits. In this case, we extract the inductances. Also, in the next slides, I will mention briefly, but for the superconducting circuits, superconducting devices or Josephson junctions can also be used to design RF digital circuits, not only analog circuits, but digital logic circuits. So between these logic circuits, we need to transfer the signals. So in this case, we use a passive transmission line, PTL. These are normally short, and they don't have to be matched to 50 ohm, or mainly matched to 2 or 3 ohms, just to transfer the superconducting pulses between two circuits. And it's also possible. And in this case, the error rate is important. So another circuit model can estimate the error rate versus frequency and the length of passive transmission line. And these models are conventional passive transmission line models. And frequency response of an RF digital circuit was measured here. And in a toggle flip-flop, which is one of the fundamental logic memory element of logic circuit. In this case, for example, we see that up to 100 gigahertz, this toggle flip-flop will operate. And after that, it will start to give wrong outputs. And before the fabrication of the circuit, so after some point, the circuit will scale quite fast, like 5 mm by 5 mm circuits that includes thousands of junctions, thousands of inductors, transmission lines, etc. So the whole chip should be simulated before fabrication. And as we know, the fabrication processes are not perfect, so they have some tolerances. Critical currents can vary up to 3 or 4%. Inductances can vary maybe up to 5%, etc. So the circuit design, RF circuit, should have enough margin to operate correctly after fabrication. Usually, it is easy to design a circuit with only a very small margin, like 0.1%. When the students first design the circuits, they are happy. They say it works, but it works only in a very slight margin. If the Josephson junction critical current fabrication is mistaken, shifts about 1%, and the circuit doesn't work. So it's good for writing a paper, but in the experiment it will not work. So you cannot use that circuit anywhere. So such analysis also should be made before the fabrication. Any questions so far? Okay. So in the case of quantum computers, unfortunately, qubits must satisfy two conflicting requirements. For example, in the case of photonic quantum computers, it's easy to isolate the qubits from the environment because the wavelength or frequency is too high and the energy is too high. In the case of superconducting qubits, they are not so robust and they are prone to environmental intervention. But since they are not very strong, entangled, then it's easy to control and measure the qubits in the case of microwave qubits or superconducting qubits. But in the case of photonic qubits, it's not easy to interact with them. So at one point, either the superconducting groups will find better ways to control and read out the qubits with low error rate, or photonic teams will find to control and access to the qubits even if they can operate very robustly. So far, everybody is trying to find good solutions, and I think there is no clear winner yet. And in between, there are some other technologies. For a transmon qubit, as I explained before, transmon qubit is basically a anharmonic oscillator with an Josephson junction used as a nonlinear inductor. Here the effect of nonlinearity, and then
Professor, just a moment, please. We couldn't hear last 2 minutes because our connection is corrupted. We couldn't hear you last 2 minutes.
From here or from here?
From where, friends? From here. Okay, yeah.
Okay. So I was in this slide I was explaining. So it's relatively easy to design individual elements, but when we make them a large chip, large circuit with 5 mm by 5 mm dimensions and thousands of junctions, the fabrication quality is not 100% perfect. So there are some tolerances in the fabrication process, like the critical currents can shift 5%, inductors can shift 5%, etc. So the designer should take into account that his circuit should work with high tolerances. So 0.1 tolerance circuit will never work when you fabricate it. So after you make sure that circuit works at one point, then you optimize the circuit so that it operates in a wide margin in terms of bias, flux levels, etc. So all the parameters should have some tolerance before you get it fabricated. And here also I asked if there are any questions so far, because I finished the first part of the lecture. Okay, no questions.
Have any questions?
Yeah.
Yes, one question. Come here, please, if you want. One of my friends will ask a question. He's coming here.
Okay.
Hi, can you hear me?
Yeah.
So from up to now, the thing I didn't quite understand is how exactly is the advantage of the superconducting chips come? And like you said, it was about there was some effects regarding the quantization of the flux, but I don't think we see the use of that. So do we work in a domain when you say currents and voltages? Do we work in a magnetic domain, or is it still similar to classical electrical currents and voltages, potentials, or?
Okay, that's a very good question. So I don't see the audience, but I assume there are students over there.
Yes.
Anybody would like to contribute to the answer this question?
No, nobody else.
Okay, so so far, so in the following slides, maybe I will try to explain your question, but to reply briefly. So far, I explained the difference of superconducting materials compared to normal metals. How it is designed by using a superconducting material. For example, a transmission line. How do you design a transmission line by using a superconducting material? Or what's the Josephson junction? But at each circuit, for example, in a digital circuit, we use one of these properties. For example, we use one flux quantization property to design a digital circuit, or use this non-linearity of the Josephson junction when we design a qubit or a parametric amplifier, or when designing a transmission line, we use the zero resistivity. Then you can design very high Q resonators. So each property has some advantage in different circuits. So I will keep this question in mind, and then when I show a device, I will explain which property of superconductivity is important in the design. So it's not, superconducting materials are not only zero resistive materials. They have quantum effects and nonlinear effects that enable quantum circuits to be developed. And if, for example, the Josephson junction did not have such a nonlinear property, we could not make a qubit by using Josephson junctions. Nonlinear effect of the Josephson junction enables this energy levels, for example. So In the previous slides, I told that Josephson junctions are good candidates for making macro-scale artificial atoms. This is enabled by this nonlinearity and anharmonic oscillator effect. And in the case of measurement side, this corresponds to, for example, 0 state corresponds to one frequency and 1 state corresponds to another frequency. So if you are in a 0 state, you measure 7 point something gigahertz, for example, and then if you are in the 1 state, you measure 8 something gigahertz. So if you can measure the state frequency of the qubit, then you can measure the state. Or if you can change the resonance frequency of the of this LC circuit, then you can control the qubit. So readout and excitations are made by RF pulses with some specific amplitude, duration, and frequency. And this is a single transmon qubit. So this is the transmon. And to interact it with the outside world, you give some qubit drive, flux bias, and then a readout resonator. And circuit model of this is like this. So this is the qubit here. You have a resonator. And then you apply some RF pulse here. And through the resonator, it's transferred to the coupled. There is a capacitor here. Capacitively coupled. Resonator is capacitively coupled to the qubit. And then you can excite the qubit from 0 state to 1 state. And then when you measure the resonance frequency, so you made some qubit operations, and then after the qubit operation, the state of the qubit has changed. Then if you read the resonance frequency, then you can see the 0 or 1 state. So in a single qubit case, it's like this. But there is no entanglement or no gate here. For example, this is a 5-qubit QPU, quantum processor. In this case, these numbers indicate the number qubit numbers. And there are some topologies. This is from IBM's tutorials. And these topologies determine which qubits are entangled with which qubits. This famous first IBM 5-qubit processor was based on this topology, but other topologies are also possible. For example, if you went a high T1 time or T2 time, then this seems to be more suitable. But then the entanglement between qubits are not so high. In this case, for example, how 0 and 1 qubit are entangled? You put a resonator in between. So there is 1 qubit here and another qubit here, and you put a resonator in between and you entangle them. And here another resonator, this line, this line. For example, you cannot make a calculation between 1 and 3 because there is no resonator here. Then when I explain this, especially the electrical engineering students coming from semiconductor logic design courses, they ask me, where is the gate? Because in a CMOS circuit, when you design a logic gate, you see the AND gate, OR gate, etc. gates physically on the chip. But here we don't see any gates. We have only qubits and resonators. Where is the gate here? Anyone can reply? So in the superconducting qubit, the gates are on the time domain. So a gate, for example, a rotation, 90-degree rotation in the x-axis from this coordinate on the Bozbey. If you want to go this coordinate on the Bozbey, you apply some microwave pulse, and then that microwave pulse enables the state from this point to this point. So this pulse corresponds to an x90 gate. Or if you want to rotate on the Bozbey in the y-axis on 90 degrees, you apply another pulse with different specifications. So actually the gate operation on the superconducting qubit means applying the correct pulses to the correct qubits. In this case, for example, if you want to implement this quantum circuit, you apply these RF pulses at this times with some specific durations. So when you have this QPU and when you have this input pulses, you implement this logic gate. Is it clear? And a quantum programmer does not need to know the microwave pulse durations, amplitudes to implement some specific gate. And in that case, for example, when you write a program in the C or Python, etc., there's a compiler and assembler, right? The computer programmer does not need to know the assembly language or machine language. That's ones and zeros. You just write your C code, and the compiler and assembler makes the conversion to machine language. In this case, there is a assembler also, which is called quantum assembler, QASM. Then when you write this code, it knows that there is a Hadamard gate and CX gate here, and then the assembler knows which RF pulses should be applied to which qubits with which parameters. So the assembler knows these parameters. So when you have a qubit and then when you want to implement it in a system, then first you characterize your qubit chip, and then you determine the correct pulses, and then assembler knows that pulses, and then user does not care about the rest anymore. The user just writes the code, and then correct pulses are sent in correct timings. And at the heart of the transmon qubit, there is this Josephson junction. Here you see a cross, very thin two cross lines, and they are, in this case, it's aluminum. There is an aluminum in this line direction, and in between there is aluminum oxide, and then there is another thin line, again aluminum. So you have aluminum oxide, and aluminum. So it's a Josephson junction. And why do we need to operate the superconducting qubits at 10-20 millikelvin temperatures? Because they operate at 5 gigahertz, 8 gigahertz, and the thermal noise corresponding to these frequencies is 240 millikelvin and 300 millikelvin. So above this temperature, the thermal noise is more dominant than the energy of the qubit, these energy levels. That's why you can operate the photonic quantum circuits in room temperatures, because they operate at much higher temperature frequencies, and their energy are above room temperature. So if you operate it at 20 millikelvin, then you operate it maybe 10 times lower than the terminal noise, which is okay. And you cannot operate them at much higher temperatures. But if you increase now some groups are also working to to operate the qubits, superconducting qubits at higher temperatures like 50 gigahertz or so. Then the operating temperature can be increased by 10 times. But this is very fundamental research now, and then still the most common operating temperatures are below 10 gigahertz. And these two pictures are famous pictures available on the internet. Unfortunately, quantum processor is just this 2 by 2 centimeter chip. The rest is just cables and cryocooler and some circulators or other RF components. So the bulkiness of the superconducting quantum computer does not come from the quantum processor, but it's peripheral room temperature electronics and the cryocooler. I think this is 128, 130 or something like that qubit of IBM. And you see it's a big room size computer. So now the challenge is to scale down this bulky electronics and cables to smaller scale, and preferably inside the cryostat. Then you don't need any cables going out of the cryostat. So in some groups are working on CMOS, cryo-CMOS technologies. Some groups are working on superconducting control electronics. But the motivation is just to get rid of all these bulky electronics and put them in the 4 Kelvin stage or millikelvin stages. Then the scalability of the superconducting quantum computers will make a leap. Because now it's limited by the number of cables that you can take out of the cryostat. Each qubit needs 4 microwave cables. If you are targeting a 100,000 qubit computer, you need 400,000 cables going out, which is not possible with meaningful dimensions. So how is it possible to make an integrated qubit readout and control circuit? In a usual quantum computer, there are such RF blocks. This is the QPU, and bias tees, filters, circulators, LNAs, amplifiers, etc. in the cryostat. And outside, there are microwave generators and digitizers, down converters, etc. So if we can make these blocks and the outside electronics on chip, then it will be possible to make a more compact and more scalable quantum computer in the future. So we are now trying to develop these building blocks, including the outside electronics. In this lecture, I will talk about a parametric amplifier and then SFQ logic for integrated qubit control and readout. So as I explained, to read out and to excite the qubit, we need some specific type of pulse with, let's say, 1 microsecond duration and minus 100 dB amplitude, etc., and 7 gigahertz frequency. This is very easy to achieve with some room temperature arbitrary waveform generator. But the question is, can we make this on chip with superconducting circuits? So we tried to design the circuit. Then by using Josephson circuits, we designed a ring oscillator. Ring oscillator is a circuit when you trigger it, it starts oscillation with some frequency based on your timing design. In this case, there are 3 circuits, 3.7, 4.2, and 5 gigahertz. So the train of pulses are at these frequencies. So now we have an RF source, but we cannot control them yet. We have just a train of pulses. Then, if we want to control the duration, since the duration is in the range of microseconds or megahertz, so it's a low frequency signal, we can use external modulation because it's easy to feed low frequency signals. You don't need expensive and bulky RF cables for such frequencies. We have an external modulation circuit. Then you adjust the duration, on duration and off duration of the circuit by some pulse generator, outside pulse generator. Then if you multiply this modulation signal and pulse train, you can get such an output. So by adjusting the on duration of the modulator, you can now determine the duration of the pulse. But still we don't have any control over the amplitude. So in that case, if we use a serial squid stack as an amplifier, then we can control the amplitude of that. If this is a programmable amplifier, then you can choose 4, 3, 2, or 1 gain in this amplifier. Then you can adjust the amplitude. But still this does not look like a microwave. This is like a train of pulses still. Then we need to filter it. After we filter it with a low pass filter, we get this microwave signal. Then by programming the amplifier, squid amplifier, we can adjust the amplitude of the pulse. By programming the modulator duration, we can control the duration. So then one box is replaced with one circuit. So this is the layout of the chip. Then this is just 2 millimeters by 1 millimeter circuit. And the good thing is it operates at 4 Kelvin. So you don't need to go outside. You can just go up to 4 Kelvin. Then you can control your qubits. This is the squid amplifier that I mentioned. Here is the squid. There are 2 Josephson junctions and 1 superconducting loop here, and serially connected for circuits. And by enabling and disabling these squids, you can control the amplitude. This is left side is the simulation and right side is the experimental data. So the simulation and experiment quite fits to each other. And now this is a building block. So we can use this in this circuit or any other circuit. In the first slide, I explained that one of the most important things is to generate the models and then building blocks of the circuits. Then this is one piece of Lego. And this is the FFT output of this microwave generator. When we take the FFT, we see that we get 3.75 gigahertz microwave signal with sharp frequency response. But this circuit is not enough because everything is superconducting here, including Josephson junction. So the impedances are very low. The output output impedance of this circuit is just 2-3 ohms. So when you directly connect it to qubits, which are generally designed to match 50 ohms, most of the signal will be reflected. So qubit will not see any RF signal due to mismatch. So a matching circuit should be designed from junction side to qubit side. Then 2 or 3 ohms of impedance here and 50 ohm impedance here. This is a mix of strip line and coplanar. There is a transition over there because matching from 2 ohm to 50 ohm is a very big challenge in a very limited space. So there are some fancy RF design techniques here, unfortunately. And for the readout, we need to just see the frequency. We don't need to measure the amplitude of the qubit signal if it's at 7 gigahertz or say 8 gigahertz, at 0 state or 1 state. So a simple comparator circuit with 1 bit or few bits resolution will satisfy it. And then the outputs are output currents are in the order of 100 nano or below 100 nano. So this Josephson circuit can act like a comparator circuit. In this case, in this test input, if there is a current above the threshold, then you get logic 1 at the output. If it is below the threshold, you get logic 0. So you put 2 comparators, one filtered for 7, another filtered for 8, then you can see the frequency state. Sorry. And any questions so far? So by the way, since due to limited time and this design of this Josephson circuits is a 1 semester course, I don't have time to explain how they operate, but in next semester we will be offering a superconducting electronics course. So if you are interested, so please send me an email, and then we can see if possible to make it online, or you can come to the class if you prefer. Sorry, and there was a question.
One very quick.
Can you hear me? Professor, can you hear me?
Very weak. I can hear you, but not so strong.
Just wait a moment, please. We will ask a question.
Okay.
Actually, this was one really quick question before it was the slide before this one, I guess.
Yeah.
So the test input here, the detection circuit, the test input has to be a magnetic flux, right?
Actually, magnetic flux means current.
Oh,
So they are almost same. This left side is a detector model. So this was developed to read out a detector output. So that's why we have some resistance and things like that. So please ignore the left side. The right side from the bobbin, right side is the readout circuit itself. So in the case of qubit, the left circuit will be replaced with a qubit resonator. And if you have a magnetic flux, it will be coupled to the coil, and then the coil there will be a current on the coil. So they are same thing actually.
Oh, I see. Okay, thank you. I think I understand. Okay.
Okay. And another important property of a superconducting circuit is it can make parametric amplification. So if there was no possibility of making a parametric amplifier, now it will be very difficult to read out the qubit states. Because just after the qubits, there are parametric amplifiers based on Josephson parametric amplifiers or Josephson traveling wave parametric amplifiers. So they are quantum limited amplifiers that can operate at millikelvins. So before you go to the CMOS or HAMT amplifiers, you amplify your signals about 20 dB. So it makes it possible to read out at room temperatures. So we all know parametric amplification from our childhood. This is like a swing. So when you are on the top of the swing, you push. Then on the other side, you push again. And then you increase your swing amount. So this is the same principle in the parametric amplifiers, both in optics and RF. So actually, the Josephson parametric amplifier principles are inherited from optical parametric amplifiers. They have the same principles. In optics, its nonlinear crystals are used. In microwave, Josephson junction is used as a nonlinear element. So in the case of four-way mixing, you supply a pump signal and then signal and idler frequencies are the sum of two pump frequencies. In the case of three-way mixing, you apply a pump at the higher frequencies and the sum of signal and idler is equal to the pump. And the pump energy is transferred to the signal energy. So there is very small signal and idler here, and the pump energy is transferred and the amplification is achieved. So we go back to the junction again. Here, the nonlinearity graph is shown versus the magnetic flux over the junction. And here, the magnetic flux over the junction is cosine of the magnetic flux is proportional to the inductance. Here, for example, now we put flux here, but in the previous equation, it was current. So they are interchangeably used. Current means flux in the circuits. So we try to operate the junction as a nonlinear inductor at the highly nonlinear region. So it's not good to operate it here, for example. It's better to operate towards the edge of the nonlinear, highest nonlinear point. Then this is a Josephson parametric amplifier, which has a squid. It could have be used as a one junction also, but for design flexibility, we chose a squid. Here is the squid loop. This blue line is the squid loop, and these rectangles are the Josephson junctions here. So Josephson junction and inductor makes a squid loop here. Then you supply your pump signal inductively coupled to the squid with 2 times or I mean with higher frequency or in between the signal and either signals. Then the signal to be amplified is fed from here. It's coupled to the squid, capacitively coupled to the squid. And with the help of the pump signal, you generate another microwave signal here, then it reflects, and from the same port, then you measure this signal and idler outputs. Then when you filter them, because they will be at different frequencies, when you filter them, you can get the idlers and signal output, amplified signals. And this is the simulation result, around 8.5 gigahertz, and it's in simulation it's possible to achieve about 20 dB of gain at microwave frequencies, and with quantum limited noise. And now we measured this circuit after we get it from the foundry. And for three-way mixing, we used such a block diagram. And for four-way mixing experiments, we use such a block diagram. And in both cases, it operated. So when you supply a signal and pump, you get the amplified output in both pump, in both three-way mixing and four-way mixing modes. So I come back to this slide. For on the left side, you design the cells once. You design the circuits, basic circuits once. So if you have a parametric amplifier that's characterized and performing okay, now you have the chip of that and model of that, layout of that. So it's in the library. And if you have a matching circuit from 2 ohm to 50 ohm, it's in the library. Then RF design or quantum circuit design is just combining them and then making another simulation optimization step before fabrication. Since they are already verified, then you don't need to verify everything from beginning. But to be able to include them in the library, many iterations may be needed. For example, you design this circuit, you send to fabrication, it does not work, or it works, but it does not fit to the simulation. Then you try to find if the model was wrong or the fabrication was wrong, and then another iteration, another iteration. After everything is fitting, then you put it in your library. Then you work from this point to the right. So in summary, in principle, almost not all maybe, but almost all the RF and photonic analog components can be implemented by using active and passive superconducting circuits. And superconducting devices have the advantage of demonstrating quantum effects at microscopic scale. And the good part is you can get them fabricated in commercial foundries or with some standard VLSI processes. And superconducting RF and quantum circuit designers do not invent the wheel from the scratch. They use the fundamental know-how from classical RF design and optical counterparts. So there is already available know-how, many years accumulated know-how in classical RF design and optical counterparts. And so far, there are many qubit technologies, alternatives, but the superconducting qubits seem to be the most mature so far. And then the big companies are able to satisfy their roadmaps. And by 2028 or 30s, I think we will start to see some useful applications based on the transmon quantum computers. Because now everybody is focusing on the scale up of the number of qubits. but without compromising the fidelities and coherence times. So sometimes it's possible to scale up with some integrated readout, but fidelities are not as good as room temperature electronics, so they are not practical. Then they try to keep the fidelities and coherence times high, but make the integrated electronics. And so far, the Josephson circuits, Josephson logic circuits, seem to be the most promising candidates for implementing an integrated superconducting QPU. The other alternative is cryo-CMOS, but the major companies are now focusing on the super Josephson circuits. So thank you. I think if you have any questions, I can answer.
Thank you very much. Yes, we are waiting for your questions. Is there any question?